today a little bit about the fast mobile measurements that we were doing in part of the Breathe London pilot project over the last few years, um, and how that can now be taken forward, and also the introduction of measurements of carbon dioxide in the ambient situation as well, which actually came up in the conversation on one of the sessions yesterday. So without any further ado, Shona, it's all yours.
Thank you. Yeah, thanks for the introduction. So I've actually got a slightly different talk title to what is in the programme. So I'll just read the new one out. So what I'm going to talk about is new insights into vehicle emissions using mobile measurements. So it's essentially all about getting more information out of mobile measurements. So if I can just have the next slide, please. So just to start with a bit of background, most of you will be aware that the WHO published new guidelines for air quality last month. So the guideline for PM 2.5 was halved, whilst that for NO2 is now 75% lower. And this is going to be a huge challenge and really piles on the pressure for countries to keep reducing air pollution below current levels. And there's really not going to be a single one-size-fits-all solution. It's going to be much more about where we can make smaller gains and how in combination these may help us to reduce overall air pollution. And so it's probably going to require a much more nuanced approach in how we target specific sources, particularly in policy development. And obviously in terms of sources, road transport still accounts for a significant proportion of emissions of all the key pollutants, and it's going to be a crucial area to target in order for us to achieve the new guidelines. So really understanding the detail surrounding vehicular sources, and particularly their spatial distribution, will be essential going forwards. And that in itself presents a lot of challenges, such as understanding real-world emissions and also the role of different after-treatment technologies. And then there's also a lot of variation in emissions depending on other factors, such as vehicle specification, driver behaviour, but also environmental factors such as ambient temperature. And all of these, really, we need to understand these in order for us to make the most effective decisions on how to reduce emissions. Next slide, please. So typically our understanding of air pollution is currently dependent on stationary measurements from monitoring site networks, but we're always striving for measurements at sort of a higher temporal and spatial resolution. And mobile measurements provide a way for us to do that. However, drawing quantitative conclusions from this type of data can be quite challenging. So currently the most common way of doing this is to split up the road network into discrete segments. So that's illustrated on the plot on the right here, just taken from the literature. And then to calculate some sort of summary statistics from each segment. And this can be useful in terms of identifying emissions hotspots or persistent sources. However, the choice of the segment length is typically quite an arbitrary choice. And it also assumes no influence of what's happening in one segment on what's happening in another. So the goal of this work really is to try and develop a method that will allow us to extract more quantitative information out of mobile measurements and ultimately establish a stronger link between concentrations that we measure and emissions. So can I have the next slide, please? So essentially what we want to do is to try and configure the analysis of mobile data in a way that allows us to apply a range of statistical methods to give us an improved understanding of emissions and their impacts. And we've kind of broken this down into a couple of key steps. So the first being that we need a way of processing data from multiple passes, so maybe multiple drives around a city on different days, as a single data set. And ideally we want to try and avoid splitting the road network up into these discrete segments. So instead we kind of want to adopt a more continuous approach. So we want to be able to treat mobile data using like a continuous window that allows us to include the influence of neighbouring points. And so one way we can do this is by applying regression techniques to the data. So you can kind of think about this almost like if you were applying a rolling regression in a trend analysis. And it could be an ordinary linear regression, so just looking at the ratio between two variables. But it could also be extended to other forms, such as quantile regression or GAMs or random forests. And I think that one of the key aspects of this sort of framework is that regression models can take into account other variables. So we can control for a lot of other things within this framework, such as vehicle speed or road type or whatever, wind speed, wind direction, whatever it may be, which may allow us to sort of look at some more interesting things. And then a final sort of benefit of this is that it would also allow us to quantify and plot uncertainties. So there may be areas where we're more uncertain about emissions than others, which may be interesting to look at. So next slide, please. So just a brief outline of the talk. So I'm just going to talk a little bit about the framework that we've begun to develop. And this is very much a work in progress. We've kind of only been looking at this for a couple of months. And then I'll try and illustrate how this sort of approach might be useful with two examples. So one based from some data in York, and then one based on some data in Manchester. So next slide, please. Can I show the next one, please? Oh, thank you. So I'll just briefly mention the data that I've used in this talk. So it was all collected using the University of York's mobile monitoring platform, where there's a nice schematic in the corner here. This is just an instrumented van capable of measuring VOCs using SIFT-MS. We've got NO and O2 instruments. We can measure greenhouse gases, so that's methane, CO2. And then we've got meteorological parameters such as wind speed and direction. And then importantly, we're fitted with a GPS for the spatial information and vehicle speed. And so this was used on numerous monitoring campaigns in the UK, based in both York and Manchester. And so I'm just going to use some of that data today. Next slide, please. So in order to be able to apply this type of regression analyses that I mentioned earlier using this sort of continuous window, you essentially need your data has to be ordered according to some variable. So if you're going to do this in a trend analysis, this would typically be time. But for mobile measurements, we're generally interested in the spatial variation and not necessarily the temporal variation. So what we can do is process the data so that it represents a single route and a measure of the distance along that route. And then what we can do is combine many repeats of the same route, so different drives over different days, into a single data set. And then essentially what you get is that a certain distance along that route then corresponds to a specific location, a specific point on the road. So just to illustrate this is an example of just a route that we defined in York. And this route or similar was repeated 30 times. So onto the next slide, please. And then essentially what we can do is we can join all of our observations to a point on that route, which allows us to express all of our measurements in terms of a distance along that route. So this plot shows what happens if you do that. So this is just methane on the Y against total distance along the route for all the 30 drives that we did. And the colours here are just the different roads. But essentially what you can see is that there's consistent enhancements at the same road position. But what this gives us is a single data set that we can now work with and apply some more advanced analysis to. So the next slide, please. So now we can consider all of our variables in terms of distance along this route. So essentially gives us a way of ordering the data. And this allows us to apply a continuous regression to the entire route. But rather than applying a single linear fit of just distance versus concentration across the whole route, it's not very useful. We essentially need a way of moving along the route to retain the spatial information. And so what we can do is employ a form of weighting function, such as a Gaussian kernel, to our regression. And I'll illustrate this on the next slide, please. So for example, if we use a Gaussian kernel function, we can essentially assign weights to each of our observations and then just move the kernel along the route at a fixed interval. So it might be every 5, every 10 meters along this route. So this plot just shows a sort of schematic to help me try and explain this. So this is just the variation in concentration of a species, just X, as a function of distance along the route. And then the points are coloured by the weight that each observation is given according to the Gaussian function. So that's overlaid in the black there. And essentially what happens is, if you're interested in a particular distance along a route, points close to that sort of distance you're interested in are weighted higher than those further away. So if you were halfway along the route, as I've shown here, the observations, maybe 100, 200 meters either side, would be weighted much higher than those at the start or the end of the route, which would be used in the regression but would essentially have no influence. And then we can also control the weighting that each observation is given by varying the width of this kernel. And I think this is where the flexibility of this method comes in. So if we look at the top panel here, we've got a really small sigma and a very narrow weighting function. And so you can imagine that this could be used to look at localized effects, whereas if we make sigma larger, so if we look at the bottom panel there, you can see that this could be used to see how things vary on a much broader, more regional scale. Next slide, please. And then just to show you, we can also visualize this on a map. So this is just the simplified road network in York with the route overlaid. And so again, you can see we've got a small and a large sigma, which essentially varying sigma just allows you to change the spatial scale over which the observations influence the regression. And that can be quite useful for evaluating the characteristics of certain sources. Next slide, please. So I can illustrate this with some actual data. So this plot shows the toluene to benzene ratio calculated along the route in York, just using simple linear regression in this case. And then the colours represent the various values of sigma that I've used. And hopefully what you can see here is that using a small sigma, so in the yellow, really exposes the localised spikes in the ratio and allows us to look at sort of fine detail of how the emissions might vary. Whereas the large sigma, so maybe the blue or the red, can be used to look at much wider regions of enhancement. So that might be how the ratio varies along an entire stretch of road compared to another, or we were thinking about applying this to some of the Breed London data. So it might be how different zones of a city sort of have different characteristics from one another. Next slide, please. So yeah, one of the real benefits of sort of configuring the data in this way is that it offers a lot of flexibility in terms of how we can analyze the data. So within the same framework, we can apply a range of different techniques depending on what we're interested in and how we want to examine the sources. So this plot here just shows how we can extract more information about vehicle sources by applying quantile regression to our observations along our route. So again, this is the toluene to benzene ratio along the entire route in York. And by using quantile regression, we can essentially see how the ratio of the two species varies across the entire distribution of concentrations, which I'm not going to go into too much detail, but essentially allows us to identify like infrequent high concentration events that might be missed if we just looked at the mean as in a normal linear regression. So in this case, and just really to demonstrate the point, we can see in the black circle here a clear enhancement at the higher percentiles at about 14k along the route. And that suggests an additional source that's got this distinctively high toluene to benzene ratio. But then because through this method we've retained the spatial information of our data, we can essentially just plot these straight back onto a map. So if I can have the next slide, please. So here, this is the 95th percentile from the previous plot. And we've just plotted the data back along our route. And you can see a clear enhancement at a specific point in the map. And so if we look at that in a bit more detail, obviously we know York very well. This is essentially a petrol station. And so that's pretty strong evidence that here we're measuring sort of these evaporative emissions, which are rich in toluene, rather than tailpipe emissions. And I think this is a nice example of how this method allows us to identify the individual sources of emissions and really start to separate them out. Can I have the next slide, please? And then I've just got sort of a shorter second example. So we were really interested in sort of the details surrounding vehicle emissions. So one of the questions that we might ask is, can we use this framework to essentially establish spatially variable fleet emission factors? And so one of the things that we commonly look at is the NOx to CO2 ratio. And so we've tried to apply this by looking at some data from Manchester. So this is just the route on the map here that we took. Just the next slide, please. And so what we can do is similar to what I just showed before in York, is we can look at how the NOx to CO2 ratio varies around Manchester. So this plot shows the ratio calculated using ordinary linear regression and a sigma value of just 20 meters. So we're really looking at how the ratio varies on quite a fine spatial scale here. And we can pick up one feature where we see an enhancement in the ratio on this particular stretch of road. So that's Wharfside Way. And this is an area where there's quite a lot of goods and logistical depots, like quite a lot of freight. So we expect quite a high volume of HGVs to be present, and they typically emit like a higher NOx to CO2 ratio. So we can look at this in a bit more detail on the next slide, please. So if we just plot the ratio along that particular road, so this is the distance along the route, but just for Wharfside Way, and then the NOx to CO2 ratio. And then the grey shaded area shows the location of the logistics depot on this road, and we can see a clear change in the ratio that corresponds to the location of that depot. And then we're quite interested in to link our measurements to emissions, so we can start to do this by comparing it to some known emission ratios. So in this case, the solid coloured lines represent the NOx to CO2 ratio for a range of different vehicles taken from one of David Carlsworth's papers, and the dashed lines are just the upper and lower bounds on the uncertainty. Well, this kind of shows that for the majority of the road, the ratio is typically representative of sort of the average fleet, so petrol and diesel passenger cars. However, when we pass the depot, the ratio is much higher and more similar to what we'd expect from heavy or light good vehicles. So this is kind of early days, and it was more me picking out sort of interesting features from this, but it may indicate how we can use this sort of method to look at the spatial pattern in emissions rather than just concentrations. So next slide, please. Yeah, so finally, just to conclude what I've said really, processing mobile observations in terms of distance along a route can open up different analysis possibilities and might allow us to apply regression techniques to spatial data. We can retain the spatial element of the data by using weighting functions within our regression. And then it allows us to examine emission sources in much more detail, offers a lot of flexibility in the methods that we can use, and allows us to investigate the spatial variation in emission factors. Just next slide, please. So yeah, thank you for listening. A couple of acknowledgements there, and any questions would be most welcome.
Shona, thank you very much. It's great to see some of the work that came out of London being carried on in this way, and I'm pleased to see that you're addressing some of the challenges that we faced and making sense of the data that we were getting from the Google cars back then. A couple of questions from me and a couple from the audience as well that are coming in. You talked about the distance along the route, being able to fix the data spatially, but how do you unpick the time of day of each drive, and also the type and volume of traffic that you may have experienced in each of the different drives? When you amass the 30 drives together, do you have mechanisms for dealing with those variations which are going to detract from the spatial signal?
So yeah, so I think within this sort of framework, we're not losing the sort of the temporal information. So we still have the dates and times of every single observation that we have. So I think the kind of idea is that if we wanted to account for time of day or season, we can do that within a regression framework. Um, or alternatively, if we are interested in just a single day, we can also look at that. And I think the same goes for sort of the traffic flow. I think one of the key aims of this project is to look at the effect of congestion. And so I think further down the line, and once we've sort of got these methods tried and tested, is can we come up with some sort of metric to account for that within the models? So I think something along those lines is how we do it.
Yeah, I mean, I think questions coming in from the are speaking to this in that if you are following a particularly dirty vehicle immediately in front of you, obviously that's something that needs to. We saw it in the London data on occasions where it was very difficult to unpick the sort of surrounding concentrations. But of course, the thing to be remembered here, looking at ratio of CO2 to NOx and due to other combustion pollutants, not necessarily the observed concentration in isolation. You want to just emphasize?
I'm sorry, the stream's a bit.
Yeah, sorry. Let me put it another way as well. People are commenting here that the fact driving along a road, measuring concentrations in a vehicle, which are likely to be higher because higher than the exposure level of the people in that vicinity. But I think that falls to the fact that you're looking at the ratio of CO2 to the criteria pollutants and not simply the observed concentration. Would you like to explain a little bit more about that?
Yeah, so I think we want to be able to. We're not necessarily looking at the actual absolute enhancements that we're seeing. We're more interested in the ratio of the emissions. And I think as well, there's obviously a question to ask about how many sort of repeats of the same route you need to be representative of sort of what we're saying might be a fleet average. So you can imagine if you had enough repeats of the same road, if you followed a dirty vehicle once, it's not going to have so much influence. And that's something that we've not necessarily thought too much about yet. But you're right, we accept that it is something that we do need to consider.
Yeah, and I think that the main outcome of what you're trying to do here is to understand the vehicle emissions from the fleet over time, and it's the ratio of those emissions that are important rather than the absolute observed concentrations. I think there has been a lot of cities around the world deploying small sensors on vehicles and driving around trying to get a handle on exposure patterns in those cities. And I think that is much more challenging because there are so many different effects, especially with particles when it comes to isokinetic sampling on the move, especially in the larger fractions. Someone has asked here about do you ever measure PM in the mobile unit? PM 2.5, PM 10, or any of the other fractions. Have you looked at that so far, Shona?
At the moment, no. We've just got gas phase instrumentation at the moment. I think there is some interest in York to see if we could maybe put a PM instrument in the van, but not as of yet, no.
Yeah. Again, in London, to try and help answer the question from the audience is, yes, we did measure particles, but we paid no heed to isokinetics at all. We assumed that we were going to lose some of the coarse fraction in PM10. But most of the PM 2.5 would be captured because PM 2.5 particles are small enough to turn corners. And of course, when you're driving along through a plume of particles, it is extremely difficult to get a representative sample in the way that we tried to do with Google Cars, but with a clear understanding at the outset that we weren't going to achieve it. So the data is what the data is, I think.
Yeah.
Yeah, it'd be interesting to see if you do integrate particles at some point, and there's a lot of learnings I think came out of London, which you have access to. I'm sure would inform that process. Just looking at the other questions coming in here, there's a question about the possibility of, again, I think this is about exposure measurement rather than emissions ratio measurement, but did you consider the possibility of using bicycles as well as the large vehicle in order to get a feel for how the gradient of concentrations vary back from the road, from the centre of the road?
In short, no, but I do quite like the idea, and I've seen some work that was done in Leeds when they managed to map a lot of Leeds using a bicycle, and yeah, and it does work well. I think the main barrier to that is we've got to measure VOCs. We've got a massive SIFT MS on there, so I'm not sure how you put that on a bike.
That was my first thought, yes.
So probably not, and we've got the van set up now anyway. But I think it depends what question you're trying to ask as well. You can't necessarily answer them all at once. I think we have to pick and choose carefully about the questions we ask and how we answer them and what data we need to do that. So.
Yeah, I think even on a big cargo bike you'd have trouble. But I suspect there is a lot of cycling goes on in York, and I think there was bicycles used in Cambridge as well, where I think Rod did some work on cycles initially to try and get the spatial information. But again, it all comes down to the type of sensors and the questions that you're asking. So there's a question here. What's the importance of measuring methane along roads?
So I think the methane was sort of a legacy instrument for this project, but previously we did studies looking at sort of oil and gas infrastructure, so trying to identify sort of maybe like leaks from the gas network on the roadside. So that was originally why we had methane. And also as well, we're not just measuring vehicle emissions. Within the ambient measurements, we've got all sorts of other sources. If we drive past a farm, we can usually pick that up. So I guess, in a way, the more measurements you have, you can kind of use that to understand the observations that you're looking at. And so methane can be quite a good tracer for other things as well.